Hello, this is part 2 of hash tables. Chaining is a way of resolving collisions in open hash tables. Each slot can hold more than one item, so this is different from the other hash tables that we looked at. It does this by creating an ordered list within each slot, so you can keep putting things in. After we get a result from our hash function, whereas in previous examples, if we had something mapped to here and then something else mapped to here, there would be a process of rehashing where it would be moved to another slot, or in the case of linear probing, or in the case of quadratic probing, would space things out a lot more. This differs in respects that instead of moving it, we now create a list. Let's say we have something mapped to 1. We have one item in that list, but then if we do our hash function and we get another one, we just link it to the other item on the list. So we just add it. And this can keep going. And you can have lots of entries in one place. So we have an entry here, maybe there's another one here, and this list could be shorter or even larger, and there may be another one over here, and this has a list. This list has to be sorted in order, so it's an ordered list. And this is how the collisions are resolved. So rather than moving things to a different slot, they're added to the slot. And this is somewhat like a filing drawer, where you look in the drawer and then you look to see where the item is that you're looking for. The advantages to doing things this way is that your table can keep on growing. You can keep on adding entries into your hash table, and then its size is not too much of a problem. If you can imagine, if I just erase some of this, if you can imagine that you've got your table, and let's say it's a regular kind of hash table and you're not using a linked list, then it can only really be a certain size, because your entries are going to fill up. If you resize it, which you can do, but if you're resizing it all of the time, your hash function is going to change. Because if you remember, we have the value, and this, we take the modulus and we use the size of the table. So here this is 11, Incidentally, it's best to use an odd size table because this helps to reduce clustering. So if I resize the table, I then have to rehash all of the entries. Because the size of the table has changed. So because the regular hash table will have just a certain amount of entries in, it quickly fills up. Whereas with chaining, you can end up with more entries in a list or more entries in your table than you have number of slots. One of the disadvantages is if you keep getting a hash function that comes up with 2, and then all of your entries are in 2, this is no different than from searching a list, which isn't much help at all. So it does require that the data entries be spread out a bit. What if our key, the thing we're going to turn into a hash function, is not an integer? Perhaps it's a string. So what if it's a Tony? What do we do then? Well, let's have a look at something interesting. Let's use this function and put a t in there, and we're going to want to print that out. And I run that. Something interesting happens. I get this 84 here. Let's make that bigger. I get this 84 here. So let's see if it's case sensitive. Now when I run it, I get a different integer. And it doesn't matter what you put in there, you will get a unique integer. So how can we make use of that? Well, if we have a variable name equals Tony, and now we want to run through it, we want to iterate through for I in range for the length of the list of name. Let me show you what the list does here. So if I do this name, and I have to print that out. See how it's split these up into their individual characters. So that's quite useful. So if I carry, so that's what's going to happen there is it's going to split this list up and it's going to iterate through each of the characters. So if I do num equals name I, so it's going to pop it into a variable. Do the code and use the ORD function and pop that variable into it. Now, if we print out encode, now we get the letter, which is this name I, and we also get its corresponding integer, which is the code that we got from ORD. So now we can add them together. So if we do total equals total plus code, and I'll have to put make a variable total. And then we would have to print this out. So if I print it out at the end, something like total is, and then total. And then we run it. And I see my error there. And then we run it. We see that total is 426. So it's added them together. So we can make integer out of the name Tony. There could be cases when you end up with the same value, so it's not exactly unique. The uniqueness is in each of the characters, but once you start adding them together, you may get the same value. Here's an example. Lambda, which is the load factor, equals the number of entries, which is 1, 2, 3, 4, divided by the size of the table. Well, the size of the table here is 11. This roughly equals 1.36. So this here This is our load factor, and it's giving us some information about how full this table is. So, the efficiency of the table is going to slow down. The more of the cells are filled up, as we said before, it becomes inefficient. So if we make the table really big and have few entries, then that's going to solve the problem, right? Well, if you think about it, when we declare the size of a table, what we're going to be doing is taking up memory. This memory is going to be wasted if we don't use it, because each one of these cells here needs memory. Also, if you think about hash tables with chaining to resolve the collisions, they have more entries in than have slots. So you could get a value that's bigger than 1. In the best case scenario, the comparisons are run in constant time, which is fantastic. Collisions complicate comparisons, though. So if a load factor is small, there is a lower chance of collisions, which is good. If the load factor is large, this will slow things down because of the collisions that happen. For open addressing with linear probing, a successful search, the number of comparisons is going to be this formula here. And this is an average case. Successful search number for comparisons is going to be the equation below. And again, that is in an average case. If chaining is being used to resolve the collisions, a successful search, the comparisons will be this expression on average, and unsuccessful search is merely just lambda, which is the load factor.
If you liked this video, give it a thumbs up and try out one of my other videos.